That's the first thing. So taking a look and saying a banana is equal to a white potato, is equal to a bowl of white rice, is equal to a bowl of pasta, is equal to a Coca-Cola. And all of those foods metabolize to this stuff called table sugar is a fundamentally flawed way of looking at a carbohydrate. Okay. So this argument basically places this idea that table sugar is bad for you. I know table sugar is bad for you. The ketogenic world knows table sugar is bad for you. You know table sugar is bad for you. Nobody should be talking about table sugar. Like, we should just move on from that, because we realize that's not the right thing to be talking about. But these foods don't metabolize to table sugar. They metabolize to a molecule or collection of molecules named glucose and fructose, which have fundamentally different behaviors than white table sugar that you see on the screen. So these foods don't metabolize to white table sugar. And in addition to that, they don't actually increase your insulin use, because you have to be more complex. You're not eating foods in isolation in most situations. And the other foods that you eat along with these foods are going to eventually determine what happens to your pancreas and how much insulin you're secreting. Okay. So in the world of diabetes, there's multiple different flavors. We got the autoimmune varieties on the top left, type 1 and 1.5. These are both autoimmune conditions. Type 1 is what I have, what I explained earlier. Type 1.5 is the adult onset, slow progressing version of type 1 diabetes. On the right-hand side, at the top, we got prediabetes and type 2 diabetes. These are what are considered lifestyle versions of diabetes. These are types of diabetes that you can induce onto yourself dependent on your lifestyle, your choices, the food that you put in your mouth, how much food you're consuming, what type of food it is, what type of exercise you're performing, how much stress is in your lifestyle, how much alcohol do you drink, do you smoke cigarettes, and beyond. So these two versions of diabetes are considered lifestyle diabetes. And then the bottom is gestational diabetes and polycystic ovarian syndrome. And these are two forms of blood glucose irregularity that affect women. Gestational diabetes during pregnancy and polycystic ovarian syndrome, which is not a form of diabetes, but it is a blood glucose irregularity that results from a genetic condition that some women are born with called PCOS. So how do you unite all three of these different flavors, if you will, of diabetes? You got the autoimmune on the top left, you got the lifestyle on the top right, and then you have blood glucose irregulators that affect women. Okay, is there something that's common to these three different groups of diabetes? Yes or no? It turns out there is, and the thing that connects them is this thing called insulin resistance. So insulin resistance is a puzzle piece that can grow over the course of time and can shrink over the course of time, and you have full control over it. If insulin resistance grows, then your blood glucose control, whether you have autoimmune versions, whether you have lifestyle versions, or whether you have blood glucose irregularity that affects women, doesn't matter. Insulin resistance grows, blood glucose control becomes harder in all three different groups. Insulin resistance gets smaller and you become more insulin sensitive, then your blood glucose control in all three categories improves. So if you really focus not on the types of diabetes, but on the pathology of insulin resistance, then you can really begin to understand how this one condition can not only affect your blood glucose control in these three different groups of diabetes, but it actually can control your overall risk for chronic disease as a whole. That's why this is such an important message. That's why at the beginning of this presentation, I said, yes, my message is for people with diabetes, but it's also for people who don't have diabetes, because the people who don't have diabetes also can develop insulin resistance, and then it can either turn into diabetes or it can increase your risk for many other conditions. So when I was first given the task in graduate school of trying to investigate insulin resistance and induce it in laboratory animals, my professor turned to me and he said, listen, you're going to become an insulin resistance master. In order to figure that out, you're going to have to go learn how to induce insulin resistance in animals. I know how to do it. I'm not going to tell you the answer. You're going to have to go figure it out. So I said, okay, sounds like a plan. So I went into the research and I started reading paper after paper after paper. I said, how have other people done this before? What can I learn from them and how can I replicate that? So I went into the research and I started reading. And the more information I dig up about insulin resistance, whether it's in mice, whether it's in rats, whether it's in monkeys, or whether it's in humans, the story was the same for all of them. The story that I was guessing would be true in my head was that you can create insulin resistance by feeding organisms sugar. So I was expecting these papers would say that we fed animals or we fed humans a diet that was high in sugar, whether it was table sugar or high fructose corn syrup or some form of liquid sucrose. And that was going to increase their level of diabetes, and their blood glucose and insulin resistance would all go in the same direction. But the more that I delved into the research, the more that I recognized that there was a commonality between all of these papers. And the papers didn't talk about sugar. The papers didn't talk about glucose. The papers talked about this stuff called lipid, which is code for fat. Lipid, which is a classification of a type of molecule that is lipid soluble, and lipids refer to triglycerides and fatty acids and steroids. So when I started to read this, I was like, this is fascinating. Why are they talking about lipids? Lipids cause insulin resistance? That's weird, right? And then I read more, how free fatty acids inhibit glucose utilization, basically block the use of glucose in human skeletal muscle. That's interesting. They're talking about free fatty acids. Okay. Impairment of glucose tolerance, which is basically impairment of insulin sensitivity in normal adults following a lowered carbohydrate intake. Oh, well, that's interesting. You're telling me that I lower carbohydrate, increase fat, that I can suppress insulin sensitivity? That's weird, right? The role of fatty acids in the pathogenesis of insulin resistance and non-insulin dependent diabetes. It's like, why are they saying fatty acids again? They're talking about fatty acids causing insulin resistance. The mechanism of free fatty acid induced insulin resistance in humans. Well, wait a minute, this is interesting, right? And this is where it all started to come full circle for me, because I was like, wait a minute, that's what happened in me, I believe, right? I used to be eating a diet that was high in fatty acids. As a result of that, my baseline level of insulin resistance had grown so much that my blood glucose became hard to control. And then when I switched over to eating a low fat diet, I brought my fat level down, and all of a sudden my insulin sensitivity went through the roof. So I'm living proof that that story could be true. And now I was seeing it over and over and over again in the research. And as I delved into each one of these papers, they then told the same story. And the story goes like this. Insulin resistance affects two main tissues in your body. Number one, your muscle, and number two, your liver. So whenever I say the words insulin resistance, or whenever you see it online, or whenever your doctor tells you about it, or you read it in a book, okay, insulin resistance equals a dysfunction of two tissues, primarily your muscle and your liver. Okay. Now, insulin resistance, like I was saying earlier, the reason I would like you to care about it, the reason I want you to open your eyes to the idea that insulin resistance is important is because, yes, insulin resistance, like we were talking about earlier, it can affect your blood glucose control for all of the conditions that you see in orange in the top right quadrant. Okay. Type 1, 1.5, prediabetes, type 2, and gestational. All of those are negatively affected as you become more insulin resistant. But in addition to that, there's a whole bunch of other conditions that are negatively affected by insulin resistance. And there's plenty of research to back up all of these claims. So as you become more insulin resistant, your risk for many types of cancer increases. As you become more insulin resistant, your risk for many different cardiovascular abnormalities, including coronary artery disease, which directly affects your heart, hypertension, which is high blood pressure, atherosclerosis, which is the hardening of blood vessels, and high cholesterol, which is increased LDL concentrations. All of those increase your risk for a future cardiac event. Okay, for a future myocardial infarction, which is a heart attack. Okay, so as you become more insulin resistant, you are negatively impacting your cardiovascular metabolism. I know I don't want that, and I know you don't want that. As you increase your level of insulin resistance, you also increase the risk for developing obesity. That's interesting. You also increase your risk for developing fatty liver, because fatty liver disease, or non-alcoholic fatty liver disease, otherwise known as NAFLD, is caused by the excess consumption of fat in your diet, which, as we know, is also associated with the insulin resistance pathology. And we'll go into more detail about that, but they all work together. Lots of fat in your diet increases insulin resistance. That feeds your liver with too much fat, causes too much fat storage inside of your liver. And now you end up with visible nodules inside of your liver. And that can cause a significant liver dysfunction, elevated liver enzymes, and can lead you towards having to get a liver transplant if you don't correct it. So this is very important to understand. In addition, PCOS, we talked about that one earlier. Women who are born with PCOS end up becoming insulin resistant de facto. So it's a two-way relationship here. Now, Alzheimer's disease is actually another very fascinating condition, which is negatively affected by an increasing degree of insulin resistance inside of your liver and muscle. So studies are now showing, and I have two friends that, I'm actually here in Saudi Arabia to give a conference with, that are named Aisha and Dean Sherzai, who are the The leaders in Alzheimer's disease research around the world, and they have also demonstrated in their research that there is an incredibly strong connection between the degree of insulin resistance inside of your body and how it can negatively impact cognitive function and lead to cognitive decline later in life. So Alzheimer's disease is actually being classified as type 3 diabetes. And so technically speaking, I could put Alzheimer's disease up in the top right quadrant in orange because it effectively is diabetes of your brain, and you can think about it that way. And then finally, insulin resistance also negatively impacts the conditions that you see in the top left quadrant, which are conditions that when you are first diagnosed with diabetes, some doctors will tell you that these are inevitable consequences of diabetes and that it's not if, but when you are going to develop them. They tell you flat off, if you don't control this, ma'am, if you don't control this, sir, you will develop one or multiple of neuropathy, which is nerve damage, blindness, kidney failure, retinopathy, and or erectile dysfunction. It's not a fun story. It's not a fun story. I believed that story when I was first diagnosed. And I said to myself, wait a minute, I'm type 1 diabetes. You're telling me that I'm going to develop some combination of these conditions shown here in the top left? Like, I hope to God I don't. That would not be fun. But what I realized is that just because you're diagnosed with diabetes does not mean that you're going to develop any of these conditions. But if you do not correct the underlying condition of insulin resistance, which causes diabetes, if you do not make significant changes to your lifestyle and become insulin sensitive, then these red conditions tend to become much stronger and the chances of you developing them go up significantly. So again, my story here is you have control. You have 100% control. We got to get rid of this thing in the middle and make insulin resistance, insulin sensitivity, and then the degree at which it impacts all of these other conditions goes way down. And as a result, your overall chronic disease risk is significantly reduced. So take a picture of the screen if you have a phone in front of you. Okay. The reason why you develop insulin resistance is because you consume excess saturated fat in your diet. And I'm going to show you the exact mechanism why this happens. So the accumulation of excess saturated fat in your muscle and liver is what traps glucose in your blood. And that causes hyperglycemia, which is high blood glucose, and hyperinsulinemia, which is high insulin output. Okay, so excess saturated fat blocks insulin action in your muscle and your liver, and that traps glucose in your blood, which then causes high blood glucose and high insulin concentrations. So let's walk into it and figure out how this works. Okay, here's step one. Lipids enter your blood before glucose. So what does that mean? Suppose you ate a cheeseburger. You ate the cheeseburger, which is a saturated fat rich meal. Saturated fat lives inside of the red meat, and it also lives inside of the cheese. You got a little bit of vegetables like, I don't know, pickles, maybe a little bit of lettuce, maybe some tomatoes. And then you got also a refined carbohydrate bun on the top and the bottom. So this is saturated fat rich and also refined carbohydrate rich. It's a standard American diet in one meal. It's a horrendous combination of nutrients. And here's what it does to you. You consume this cheeseburger, and the saturated fat molecules, which are shown in yellow, they end up traveling down your esophagus. You chew them up in your mouth. They end up going down your esophagus. They get inside of your stomach. Inside of your stomach is basically just an acid reactor. And it throws a bunch of hydrochloric acid that's manufactured by the walls of your stomach. And it starts to unfold the proteins. It starts to prepare the nutrients inside of that food for digestion. It then passes those nutrients into your small intestine. Inside of your small intestine, you have thousands of microvilli structures, as you can see on the screen here. These microvilli structures are little fingers, and I said thousands. You have trillions of microvilli. And these microvilli are basically little fingers that they kind of look like little like octopus tentacles. And they line the inside lining of your small intestine. And so what that means is that when nutrients are moving down through the tube of your small intestine, they brush up against these microvilli structures. And when the saturated fat molecules in particular get up against this membrane, they then get absorbed through the microvilli structures and they get put into your lymph system. And then from your lymph system, they get transferred to your blood, and then they get put directly into your blood. So you can see the yellow starts in the cheeseburger. It goes to the microvilli. It ends up inside of your blood, both on the left and the right. Now, as soon as that happens, one of the things that happens is that there's a feedback mechanism directly to your stomach, and it says, hold on. I detect fat. Time to slow down, because for many reasons, fat inside of your digestive system actually slows down the rate at which your stomach empties food into the small intestine. So as a result of that, there's a whole collection of food that is undigested, that is sitting inside of your stomach, that is ready and waiting to go into your small intestine. And it basically causes a traffic jam and says, hold on. Pyloric sphincter, which is just a door that separates the two compartments. It says, hold on. I want you to stay closed. I want you to slow down a little bit. I need a little bit more time to get this fat out of the small intestine and put it in the lymph system. And you should just chill out for a little bit. So as a result of that, there's more food that ends up inside of your stomach for a longer period of time. And that gives you the sensation that you're full. You end up stopping eating. And that's one of the reasons why when you eat foods that are fat rich and tend to be protein rich as well, that you end up getting full relatively quickly, because your pyloric sphincter actually slows down, and that keeps food in your upper digestive system, which gives your brain the sensation that it has to slow down so that you don't get overfull. Okay. So what that means is that lipids get inside of your blood quickly, but yet the carbohydrate energy, which tends to be mainly inside of your stomach at this point, is absorbed very slowly. And that means that your blood glucose level doesn't have a chance to rise because it's undigested, and it's just kind of hanging out inside of your stomach for an extended period of time. Okay. So the next thing that happens is that these fatty acids that are now inside of your blood, they are put into these particles known as lipoproteins. So we don't need to geek out on lipoproteins, but just understand that they don't float by themselves. They're put into little packages. And these little packages are floating inside of your blood in the billions or the trillions. And their goal is to basically circulate through your circulatory system to get to their eventual destination. What is their eventual destination? Well, the liver is one and the muscle is the second. So these fatty acids end up getting transported to your liver and to your muscle. And the fatty acids start entering your liver and entering your muscle effectively for free. Now, your liver and muscle, the reason why they take up fatty acids is because they don't really have this very complex mechanism to block fatty acids from getting inside of both tissues. They have sort of relatively weak transport mechanisms that enable fatty acids to get in. It's not really regulated by too much. It doesn't require an escort. It doesn't have a very sophisticated, redundant backup mechanism. And so as a result of that, when there's more fat inside of your blood, there's just more fat that goes into your liver, and there's more fat that goes into your muscle. It's a process known as what's called mass action. And mass action refers to when the concentration here goes up, then the concentration here also goes up, because the amount of mass on this side forces material to move across a membrane to become more concentrated on this side of the membrane. So it's literally, you can just think of a lot of stuff here pushes a lot of stuff here and a lot of stuff there. So the fatty acids begin to accumulate inside of your liver and inside of your muscle. So what? Why is that important? So in this scenario, you also have glucose inside of your blood. And the glucose is in your blood because, again, the glucose came from the bun that you just consumed. And truth be told, glucose is always in your blood. There's always going to have to be a base level concentration. And the amount that came in from the bun is now also trying to find a home. So the glucose inside of your blood goes, hey, can I get inside the liver too? Because I don't want to stay out in the blood. That's not my goal. I'm trying to get inside of the liver. I'm trying to get inside of the muscle. So let me try and make that happen. So the glucose basically tries to get inside of your liver and tries to get inside of your muscle, but can't get inside of your liver and muscle as efficiently as before, because your liver and muscle say, hold on. I got this stuff called fat inside of me. This stuff got here first. As you can see, I'm accumulating this stuff. I didn't really ask for it. It wasn't my choice. I got to deal with this stuff first. So you know what, glucose, I need you to stay outside right now. I need you to just chill out. I'm not ready for you yet. I got to get rid of this fat. I got to oxidize these fat molecules first. And then when they're in a lower concentration, then I can start to pick you up, because I just have too much energy inside of me right now. So the glucose basically says, okay, well, in order for me to get inside of these tissues, I'm going to need an escort. And the escort is actually insulin. So truth be told, insulin is the one that tells the liver and muscle that there's glucose in the blood in the first place. So insulin comes to the liver and muscle goes, hey, knock, knock. There's some glucose inside of your blood. How about you take that stuff up right now? And the liver and muscle, again, they respond by saying, sorry, the fatty acids got here first. Like, not my design, not my control. Yeah, I got to deal with this stuff first. I'm not open for action. So as a result of that, they actually down-regulate insulin receptors. And as a result of that, when insulin comes and knocks on the door, and then knocks on the door again, and then knocks on the door again, effectively what it's trying to do is it's trying to find its insulin receptor. And it's not docking on its insulin receptor because the insulin receptor is not functioning properly. And so as a result of that, insulin is basically just struggling. It's like swimming in this ocean of extracellular fluid, and it's basically trying to get to the muscle cell and trying to get in here, trying to get in here, trying to get in here. And it can't get there because it can't dock properly. And as a result of that, it's like, man, glucose, I am trying to dock so that you can get inside. And the glucose is like, well, this is problematic because now I got nowhere to go. So the glucose ends up staying inside of your blood. So the glucose effectively gets trapped. So glucose says, all right, look, I'm stuck. The liver rejected me, the muscle rejected me. I can't really go anywhere. So that ends up causing the glucose concentration to rise because there's, over the course of time, more carbohydrates being digested from your small intestine from that bun, and more carbohydrates being, or more glucose is being put into your blood. But again, that glucose can't really find an exit route. And as a result of that, now glucose begins to accumulate. So in this scenario, your pancreas says, you know what, I think I can solve this problem because I put out a couple of insulin units. I put out a couple of insulin messengers into the blood to try and go get the liver and muscle to open their doors. That clearly didn't work because the liver and muscle, they're just not paying attention to insulin right now. So you know what? I'm going to make more insulin. So then your pancreas goes, all right, let me just manufacture more. So instead of manufacturing, call it 3 units of insulin, it then goes and manufactures an extra 2. So now you have a total of 5 units of insulin. So no, the extra 2 units of insulin come to the same muscle, same liver, and they go, knock, knock, knock. It's time to get that glucose out of the blood and inside of both of you. And at a certain point, the amount of insulin that's in your blood can effectively overpower the insulin receptors inside of your liver and muscle. If you just put enough insulin, then more insulin can more effectively translate the signal, more effectively open the doors, more effectively communicate with insulin receptors to basically say, all right, I'm taking over. I have the keys to the kingdom. Your time is to open up and let this glucose in. So your pancreas basically is here. It's the Superman of the situation that comes to save the day. The problem is that you actually have 1, 2, 3 problems simultaneously that are now accumulating at the same time. Number 1, hyperlipidemia, which is excess fat inside of your blood. This is what caused the problem in the first place. So there was a large intake, a large influx of saturated fat in a short period of time, and that caused a transient increase in the amount of lipid that's inside of your blood. That's problem number 1. Number 2, this causes a transient increase in the amount of glucose that gets trapped in your blood because the glucose can't get inside of your liver and muscle because the fatty acids beat it there. That's problem number 2. Problem number 3 is that now you have transient increased insulin inside of your blood, otherwise known as hyperinsulinemia, because your pancreas had to come solve the problem by over manufacturing insulin and working in overdrive. So fatty acids caused the problem, glucose got backed up, and then insulin had to come and save the day. Excess fat was called hyperlipidemia, excess glucose, hyperglycemia, excess insulin, hyperinsulinemia. 1, 2, triple whammy. This is insulin resistance. This is the classic game. This is the classic game that unfolds every single time you eat a meal that contains a significant amount of saturated fat. Every single time you cause a traffic jam inside of your liver and muscle, and then that backs up the glucose pathway, which causes insulin to become less effective, which causes insulin to have to be oversecreted. And if you can imagine, if you did this for breakfast, then you did it for lunch, and then you did the next day, and then you did the next day, and then the next week, and the next month, over the course of time, you're forcing your pancreas to have to work a lot harder than it's supposed to. And this is going to cause your pancreas, the beta cells that are manufacturing insulin, to eventually become very tired, very fatigued, and then they're going to commit programmed cell death called apoptosis, and they're going to go bye-bye. And then at that point, you don't have insulin production. Now you're in a pickle. Okay. So that's the first 2 steps. Now, here's what else happens. There's this other thing here called adipose tissue macrophage infiltration. I'm going to explain what this is all about. This happens mainly in people who are obese. It also happens in some lean individuals, but mainly in people who are significantly overweight with a BMI greater than 30. Okay? The research talks about this stuff called macrophage infiltration and or excess adiposity inside of inside of adipose tissue. It's written all over the research, and very few people actually talk about this because it is a highly inflammatory condition, and it can negatively impact the way that your adipose tissue functions. So you take a look at the same picture from before, okay? You got your blood on the right-hand side, you got your pancreas hanging out in the background, You got a lot of saturated fat shown here in yellow in the middle. You got a little bit of glucose and a little bit of insulin. This is the starting point from the previous picture. So these saturated fatty acid molecules, like we said, we used to have your liver and muscle over on the left-hand side because a lot of those fatty acids ended up inside of your liver and muscle, which is a true statement. But in addition to getting inside of your liver and inside of your muscle, they're also getting channeled directly into your fat tissue. So your fat tissue is actually the right place, the correct place, the safe place. It's the appropriate place to store these fatty acids. And in order to get these fatty acids inside of it, you just have to show up. And the fat tissue knows exactly what to do in order to recognize it, in order to pull it in, and in order to store it for long periods of time. So saturated fatty acid goes and knocks on the door and goes, hey, by the way, there's a lot of me in the blood. What do you want to do about it? And the fat tissue goes, all right, cool, sweet. Well, I am your home. But come inside. So the fat tissue actually starts to expand just a little bit with every single meal that you consume. And these cells, these adipose tissue cells called adipocytes, end up getting just a little bit bigger today, and then a little bit bigger tomorrow, and a little bit bigger, and a little bit bigger, and a little bit bigger over the course of time, especially when the consumption of fatty acid is puts you in a positive energy balance, meaning that you're consuming more total energy than you're expending. In other words, when you consume a high calorie diet and you're not active, that means you're accumulating energy and you're not getting rid of it. And as a result of that, you have a net excess of energy. So the excess begins to build up inside of these adipose tissue cells, and it causes them to swell. And this is called hyperplasia, when the cells become very large. And at a certain point, these cells actually swell up like a balloon, and some of them can break open. And as soon as some of these cells start to break open and store large amounts of fatty acids, it causes a huge problem, because the cells, once they break open, they spill their internal contents, their intracellular material, into the extracellular space. And as soon as that material is put in the extracellular space, then all of a sudden the tissue goes into this cytokine panic mode. All of a sudden it's like emergency, emergency, emergency. This stuff is not supposed to be outside of the cell. It's supposed to be contained inside of a cell. Why is it here? Get rid of this stuff immediately. So it starts to send out these things called cytokines. You probably have heard about cytokines when COVID-19 was around. Everybody was talking about cytokine storms because it can become this feed forward mechanism that can end up in a very, very dangerous metabolic state. So your adipose tissue sends out cytokines, and these cytokines are called TNF alpha and MIP-1 alpha. These, you don't have to remember these, but these are basically just names of these molecules that are sent out by the adipose tissue.